This is the GMAT 41. You are welcome to our ordinary differential equation class. In this video, we are going to look at the non-homogeneous second order ordinary differential equation. In a previous class, we actually have introduced this with questions solved and done. I'd like us to look at all the forms of questions and certain important concepts we should bear in mind depending on the type of question that we are presented with when dealing with non-homogeneous SOODE. The GMAT 41's interest in this class is to deal with cases whereby you have the non-homogeneous second order ordinary differential equation such that the f of x part contains exponential alpha x. I take that again. Such that the non-homogeneous second order ordinary differential equation, the f of x part contains the exponential function. So this alpha here represents a constant. Now, when we encounter a problem of this form, it's very important for us to be careful. There are several cases that could develop while you handle this problem of this form. We're going to look at 4 of these cases. In this video, 3 will be presented. In the next video, as I present the 4th case, it pleases me to introduce you to the Ohmmaker's legendary formula. Please come along with me, friends. Let's look at the first 3 cases as we have here on the board. Case 1 is a situation where the exponential alpha x is not a solution of these parts of the second order ordinary differential equation, non-homogeneous. You know, from what we learned in the previous class, when you are given a non-homogeneous second order ordinary differential equation, the general solution contains 2 parts. The complementary function part and the other part that is obtained from the particular integral. You remember, right? And so we say that the general solution y is equal to y sub c plus y sub p. So we use yp, alright, to represent the particular integral solution part of the non-homogeneous SOODE. Our interest is to focus more on the particular integral solution part, because for the y sub c part, that is the complementary function, we didn't have much problems in that. I'd already stated in the previous class that all we need to do is get a full idea of the methods of solving quadratic equation, specifically the factorization method as well as the completing the square method, alright, or the almighty formula, that's quadratic formula. So in this video, we wouldn't talk much on the complementary function part. When I bring in the complementary function part, it's for a reason, so we can be able to compare and see if that complementary function part has the exponential function that is contained in the f of x for the non-homogeneous SOODE. Now let us move on to business, okay? If you're given a problem like this, you now notice that the f of x contains exponential alpha x, that's the exponential function, is that okay? Then after solving these parts of that non-homogeneous second order differential equation, you know, solving this part is the homogeneous part, that is setting this equal to 0 and solving. You will obtain what we call the complementary function. Now, suppose this exponential part of this f of x is not a solution of this. That is to say, in other words, if it is not in the complementary function of this, then the particular integral you're expected to use to solve for the f of x part will be given as this, k exponential alpha x, which I labeled as equation 1. These are terms you have to memorize. This is telling you that you're given a problem, non-homogeneous SOODE. Now the f of x contains exponential function part. when you solve this part, making it equal to 0 and then solving to obtain the complementary function, you now notice that this exponential alpha x, the exponential part in this f of x, is not in the complementary function solution. Then, the particular integral to use is this. It's interesting to know that this equation 1 happens to be the simplest case, alright, of such kind of problem. We're going to find out how we handle all of this. But let's move on to case 2. Case 2 is in a situation where you found out that this exponential alpha x, which of course is contained in this f of x of the non-homogeneous SOODE, you find out that that exponential alpha x is a solution of this part of the non-homogeneous SOODE. That is to say, the exponential part contained in f of x happens to also appear when you solve to obtain the complementary function. It appeared in that complementary function. In that case, what will be the YP solution of the f of x part? It's no longer going to be this. This is the form it's going to take. You notice now that we've introduced x as a multiplier of the exponential alpha x. So this is the general form that YP will take. YP will be equal to k times x exponential alpha x. Case 3. Consider a case down there. After solving the homogeneous part of the non-homogeneous SOODE, that is the complementary function, you obtained the complementary function. And you now noticed that exponential alpha x and x exponential alpha x are solutions in that complementary function. They are solutions in that complementary function. What do you do? What I try to talk about here is a situation whereby the exponential term you have in this f of x appeared twice in the complementary function. When that is the case, then the yp to solve for the f of x part is going to take this form. You can see that now. Kx raised to the power 2 exponential alpha x. That's the form it's going to take now. You notice that this x is now squared. No longer this form. No longer this form. If you use any of this form to solve a problem, in the case whereby the exponential term contained in f of x appeared twice in the complementary function, the left hand side would become 0. I mean, you would get nothing. Is that okay? Now, in all three cases here, take note that k is a constant. But the constant there is not 0. That k here in all three cases is a constant, but it is not 0. Take note of that. Now, how do we solve this problem? Here in this video, I just talked about the general approach to a problem of this kind. Is that okay? The general approach, what we may see being done in most cases. All we need to do is simply to differentiate the yp 2 times. Of course, this is second order we're analyzing, so you need to differentiate 2 times. As many times as the order of the differential equation, and the order is order 2. So in each case, we're going to differentiate the particular integral general form 2 times. That's what we have y prime p and y prime prime of p. Is that okay? Or you say yp prime and yp prime prime. That's first and second order derivative of the yp you selected, as the case might be. What do you do after differentiating? 2 times. You go back to the given non-homogeneous SOODE. The value of yp, the value of yp prime, the value of yp prime prime, you simply substitute it into this left-hand side, make it equal to f of x, then simplify. Generally, the exponential term will cancel. You simplify whatever you get here, solve the equation you got there, and then you get your yp value. That yp value becomes the solution of this what? F of x. You can see that here after differentiating, you substitute. Alright? Wherever you see, this thing is y prime prime. This is the 2y d squared x. The y dx is y prime. This is y prime, y prime. So in place of this y prime, you fix in the value of yp prime. In place of this y prime, which is the y dx, you fix in the value of yp prime. In the place of this y, you fix in the value of yp for that case that you noticed while solving the problem. Okay, It is true that this happens to be the general approach to problems of this kind. However, the GMAT 41 here recommends the Unmaker's-Legendre formula. And that is why in the next video, as I introduce case 4, I should present the Unmaker's-Legendre formula that solves this problem with ease.